Hello everyone, and welcome back. Today we're going to continue our exploration of the foundations of mathematics and introduce or explore a set of numbers that are probably not common to a lot of you, especially if you don't dive deep into applied mathematics, especially at the higher level, or maybe even some physics and chemistry. So what we're going to be talking about is the set of complex numbers and some of the basic principles that you definitely should know if you plan on working with or using them. So let's just introduce a basic concept that you probably already have some general notions of, and that is solving equations. So probably the easiest equation that you probably learned how to solve would be your linear equation, which is one that can be represented in the form ax plus b is equal to 0, where a is a non-zero constant. And somebody says, okay, solve the equation 5x plus 6 is equal to 0. And you're going to be like, okay, I'm going to subtract b from both sides and divide by a. And my solution will be x is equal to minus b divided by a. And that would be your solution. Of course, if you increase the degree of that equation, for example, up to 2, we would call that a quadratic equation. Maybe you have solved these in the past, I don't know, but we'll definitely explore these in a lot of detail in the near future. But a quadratic equation is one that can be represented in the form ax squared plus bx plus c is equal to 0, where a is not equal to 0. And you're going to be like, okay, well, how can I solve this? This is a little bit more complex because I have two instances of x in this particular expression. But one can show that there is a closed form representation for the solution. In particular, you're going to have two, well, generally at most two solutions, and x is going to be equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a, which some people will refer to as the quadratic equation. But if you do not know this equation, that is perfectly okay. That is not our focus for today. So what I want to actually focus on is a special case of this quadratic equation. So our special case that we're going to be focused on is we're going to be letting b be equal to 0 in that quadratic equation. So some people will refer to this as a depressed quadratic equation. So ax squared plus c is equal to 0. Again, where a is not equal to 0. And you can sort of view this as, okay, well, it's almost like a linear equation. I'm going to subtract c from both sides, divide both sides by a, and then do something with this quadratic term of square. So if I do such that, I'm going to have x squared is equal to minus c over a, right? So keep in mind, so important note, let us assume that x is a real number. So if x is a real number, one can prove that if you square that real number, it's always going to be greater than or equal to 0, regardless of that particular value of x. So if we're interested in solving this particular quadratic equation, then if x is a real valued solution, then this number c and a cannot both be positive. Because if it were positive, then c divided by a would be positive, and negative c over a would be negative, and x squared cannot be equal to a negative quantity, right? So if c and a cannot both be positive, that means exactly one must be negative, right? Because if both were negative, then that would be equivalent to the both are positive case, which if x is a real solution, cannot exist, right? So let's just illustrate this with a basic example. Suppose we have like 5x squared minus 3 is equal to 0. So a is 5, c is negative 3, so one is positive, one is negative. So we should have at least one solution. So once we isolate, we're going to have 5x squared is equal to 3, which means that x squared is equal to 3/5. And then we can take the square root of both sides of this relation, and we're going to have that the absolute value of x is going to be equal to the square root of 3/5. And keep in mind, this is very important, that the square root of x squared is equal to the absolute value of x, because the square root returns the principal root of that particular statement underneath. In particular, the square root is always a non-negative entry, and then we have this absolute value equation, which we're definitely going to solve in a lot more detail later. But you should know that if the absolute value of x is equal to a positive number, then either x is equal to that positive number or x is equal to the opposite of that positive number, right? So these are our two solutions to this original quadratic equation, right? So let's look at a slightly different example, but instead of one being positive, one being negative, let's consider the case where both are positive. In particular, let's assume that x squared plus 1 is equal to 0. Isolating is going to give us x squared is equal to minus 1. Taking the square root of both sides is going to give us the absolute value of x is equal to the square root of minus 1. And if you remember anything about the square root relation, y is equal to the square root of x, the domain for this particular relation is going to be all non-negative real numbers, right? At least for x. Agreed? So you're like, okay, well, the square root of negative 1 doesn't exist in the real numbers, so that's problematic. But if we sort of continue this narrative, okay, well, x is either going to be the positive square root of negative 1, or x is going to be equal to the negative square root of negative 1. And those would be our two solutions. But keep in mind, the square root of negative 1 does not belong in the reals, so where does it belong? It has to belong into another set that is not necessarily a subset of R. So this is what motivates the definition of a new number. In particular, we're going to define this number I to be equal to the square root of minus 1, and then we're going to have that x is going to be equal to I as the first solution, x is going to be equal to minus I as our second solution to this quadratic equation, right? So we have that the square root of minus 1 is equal to I, so you can actually get quite a few interesting relations out of this particular thing. For example, if I square both sides, we're going to have that I squared is equal to minus 1. Because if I is a real number, then I squared cannot be equal to a negative number. So now that we have this new unit that is going to represent a basis element for a new set of numbers, now we can square these new numbers and get negative quantities back, which is very, very useful. But when we start defining new numbers and new constructs on those numbers, you have to be careful not to try and extend those properties that we have on the set of real numbers onto the set of new numbers. In fact, not all real number properties work on such numbers, right? Which should pose a concern, right? So let's just do a very quick example. So if we have the square root of a times b, you may have learned that this is equal to the square root of a times the square root of b. And maybe that's all you learned, but this is only true if a and b are non-negative real numbers, right? So if a is negative 3 or b is negative 2, this does not work, right? So I can easily pretend that, okay, well, what if I don't have this? What if I try and do it anyway? Will I get any issues, right? So we know that 1 is the same as the square root of 1, and we know that 1 is just another way of writing minus 1 times minus 1. So can we distribute the square root over this product of minus 1 and minus 1? So if we sort of ignore this rule that is actually true, then you're going to have that this is going to be the square root of negative 1 times the square root of minus 1. By definition, this is going to be equal to I times I, and I times I is going to be I squared, and we know that I squared is equal to minus 1. And you're like, okay, well, that's cool. But if you sort of zoom out, what we have here is that 1 is equal to minus 1. And if we add 1 to both sides of that equation, we have that 2 is equal to 0, which is not true at all, right? So if you try to use this property on things that are not real non-negative numbers, then you're going to generally get contradictions that are not true. So be sure to remember that this distribution of even indexed radicals only applies to radicands that are real non-negative numbers. So that is one thing that you have to keep in mind when trying to extend these properties to larger sets. So now that we have introduced this new number unit, which we denoted by I, now we're going to formally introduce this set of numbers that sort of can be built from both the real numbers and this single unit I, and that's called the set of complex numbers, which we're going to be abbreviating by fancy letter C. So the set of complex numbers, i.e. C, is the set of all numbers z, which can be expressed in the form x plus iy, where x and y are allowed to be both real numbers, and I is defined to be equal to the square root of -1. Some people will refer to I as the imaginary unit, but I is not really that imaginary. It's actually pretty real in terms of its applications, right? So it's very easy to see that if we let, for example, y be equal to 0, then z is just going to be equal to x, and x is just going to be equal to r. So it's very easy to see that the set of real numbers is a subset of the set of complex numbers. So you can sort of view the set of complex numbers here as the set containing, for example, r and, for example, IR. So R is the set of reals, IR is the set of imaginary numbers, and the reals and the imaginary numbers union together would be the set of complex numbers, right? And of course you have the, combination of the two, right? So for example, over here you have like 5, over here you have like 5i, and generally you can add these two together and you would still be in the set C. Okay, so this term x is known as the real part and y is known as the imaginary part of that number. So we're going to denote the real part of z. So we're going to denote that by re of z. So that's going to be equal to x. And then we're going to have the imaginary part of z, which we're going to denote as im of z. So this is going to be equal to y. So if we combine these two things together, we have that z can always be represented as the real part of z plus I times the imaginary part of z. And these mechanisms, re and im, are just functions that map a complex number to a real number. So we can say that re maps a z in the set of complex to some number a in the set of reals. Same for I as well, or IM. So we know how to plot real numbers on a real number line. You can actually do the same for complex numbers, but keep in mind complex numbers has two components, a real and imaginary part. So if you want to plot a complex number on a complex line, I guess you could say, it's technically equivalent to the real plane. So in the horizontal axis is going to be the real part, and this is going to be the imaginary part of that number. So if we have this point located here, this is sort of like where 3 plus 5i is going to be located, and it's sort of similar to the point 3 comma 5 that belongs to R2. But keep in mind 3 plus 5i belongs to C. So one could say, okay, well, C and R2 do share some similarities with each other, and there's actually a lot of truth to that statement. So if somebody says, okay, well, where would -10 plus 5i be located? It would be located somewhere over here, because that would be similar to the point -10 comma 5 that would belong to R2. And if I have this point here, this would be something like -3 minus 2i, that value. And for example, this point over here would be like 1 minus 2i, that complex number, which would be similar to the point 1 negative 2, and that would be similar to -3 minus 2, right? So that's how you would plot complex numbers, right? But it's important to note, as I've already mentioned, that C is similar to R2, but not equal to. Because C is a set of numbers like Z1, Z2, and Z3, and so on. But R2 is a set of points like X1, Y1, X2, Y2, and so on. So this is a set of numbers this is a set of points. And numbers are not necessarily points, but of course they do share some structural similarities, but again, they are not equal. So I just want to make that clear. So this is what complex numbers are. So obviously we can plot complex numbers, but can we add, subtract, multiply, and divide them just like we do with reals? Yes. So let's work through a few examples on how that actually goes. Now that we've defined the set of complex numbers, now what it would be nice to do is define some binary operations on this set so that we can, sort of analyze a lot of functions on this set or do some geometry on this set or several other things for that matter, right? And the first basic operation that we would probably want to define would be addition. So what we're going to do is we're going to, let us assume z1 and z2 are both complex numbers where the imaginary part is not necessarily equal to 0. So what would addition look like? So z1 plus z2, where plus is the typical addition, hopefully inherited from the set of real numbers, would be, for example, x1 plus I y1, where x1 and y1 are the real and imaginary parts of z1, and then plus x2 plus I y2, where x2 and y2 are the real and imaginary parts of z2. So what should we define this operation to be? Well, if we sort of look at what we have here, in some sense we're tempted to combine like terms, i.e. combine the real parts and combine the imaginary parts together, and in fact that's what we're going to define this to be. So it's going to be equal to x1 plus x2 plus I times y1 plus y2, right? So this is how we're going to add complex numbers. We're going to add the real parts, we're going to add the imaginary parts, and that is going to be our new complex number, because two reals added together is a real number, two real numbers added together is a real number. So we have a real number plus I times a real number, so this is obviously an element of C, i.e. C is closed under addition is what we say. So how would we define subtraction between complex numbers? So that is z1 minus z2, which has the inherent structure x1 plus I y1, and then we're going to define this operation minus on x2 plus I y2, and here, how would we define this particular structure? So one would be tempted to distribute this negative number, and indeed that's what we're going to do, and then we're going to combine real and imaginary parts just like we did with addition. So we're going to be doing x1 minus x2 and then plus I times y1 minus y2, i.e. we're going to subtract a real part and subtract our imaginary parts in that particular direction, and that's how we're going to define subtraction of complex numbers. And what about multiplication? So multiplication is going to be a little bit more involved. So this is going to be z1 times z2. And you should also be able to verify that, for example, subtraction between complex numbers will also be complex. That's actually not hard to verify. So z1 times z2, its inherent structure will be x1 plus I y1 multiplied by x2 plus I y2. So it's tempted to do the distributive property on this, and that's what we're going to do. So we're going to distribute x1 to the first and second term, and then we're going to distribute I y1 to the first and second term of that second binomial term. So once we do that, we're going to have, so we're going to define this to be equal to x1 times x2, which is defined between reals, so that's not an issue, and then plus I times x1 times y2 is what we're going to define that to be, and then plus I times y1 times x2, and over here we're going to have I times I, which is I squared, and then y1, y2. So if you remember that I is the square root of negative 1, which means that I squared is just going to be equal to minus 1. So this is going to turn into minus 1, which means that that is a negative, potentially, real number. So this is a real number and this is a real number, so we can group those things together. So we're going to have x1, x2 minus y1, y2, and then we're going to cluster our I terms together. So we're going to have plus I times x1, y2 y2 plus x2 y1. Right? So this is going to be how we're going to do multiplication on complex numbers. So let's just work through a quick numerical example. Suppose somebody says, okay, well, what is 5 plus 2i times 7 minus 6i? So we would distribute this as normal, so that's going to be 7 times 5, which is 35, 6 times 5, which is going to be 30i, and then let's pretend that that is a 2, so that's going to be 2i times 7, so that's going to be equal to 14i, and then 2i minus 6i is going to be equal to minus 12i squared. Minus 12i squared is the same as positive 12, so we just can cancel those things out. And we have that 35 plus 12 will be equal to 47, and then negative 30 plus 14 is the same as 30 minus 14, just opposite, so that's going to be equal to minus 16i, and this is going to be the result of this product of complex numbers. So multiplication isn't that difficult, so let's take a look and see how we would define division on complex numbers. So division on complex numbers. So this is actually a little bit more fun. So this is going to be z1 divided by z2, which is, in its inherent form, x1 plus iy1 over x2 plus iy2. And you're like, okay, well, it's not very clear what we're going to do here, but what we're going to do is we're going to define this to be equal to this structure, but multiplied by x2 minus iy2 and x2 minus iy2. Right? So we're just sort of multiplying by 1, which is not going to change the value, but you're actually going to see something very interesting happen here, right? So why do we multiply by this particular one? Why not multiply by the bottom, or multiply by the top, or multiply by 6, or something like that? We'll see. So we already know how to multiply complex numbers, and that's what we're doing in top and bottom. So on the top, we're going to have x1, x2 minus I x1, y2 plus x2 I y1, and then I times minus I is going to be positive 1, so we're going to have positive y1, y2 on top, and on the bottom we're going to have x2 squared minus I x2, y2 plus I y2 x2, and then minus I times I is positive y to the quantity squared. If you notice, this term and this term will cancel because they are the same but opposite signs, and the bottom is just a real number squared plus a real number squared, which is just a real number. So it eliminates the complex entity term on the bottom, which is actually pretty nice. So what we have on the top is just going to be equal to, so once we cluster our real terms together, which is just x1, x2, y1, y2, we're just going to have x1, x2 plus y1, y2 all over x2 squared plus y2 squared. And then we're going to have our I term, which is just going to be equal to x1, let's see how I want to write this. You can write it as, yeah, let's distribute our minus sign. So we're going to have, let's do x2, y1, because keep in mind we have this minus sign. Yeah, let's do x2, y1 minus x1, y2 all over x2 squared plus y2 squared. Right? And that gives you the complex representation of the division of complex numbers, because we know that x1, x2, y1, y2, these are all real, so this is just a real number. This is just a real number, so we have real plus I real, which we know is going to be a complex number, so everything checks out. Let's just work through a numerical example just to make sure we understand this more abstract representation of division. So let's assume that we have 5 plus 2i divided by 7 minus 6i, and somebody says write this in standard form, which is just a plus bi, where a and b are reals. So what we're going to do is we're going to multiply top and bottom by the bottom, but instead of minus, we're going to do plus. So 7 plus 6i, 7 plus 6i. If it was plus, we would switch to a minus sign. So this is going to be equal to what? So 7 times 5 is just going to be 35. 5 times 6 is going to be equal to 30. 2 times 7 is going to be equal to 14. And 2 times 6 is going to be 12, and that's going to change to a minus 12 because of the I squared. On the bottom, we're going to have 49. 7 times 6 is 42i. 7 times 6 is 42i, but negative. And 6 times 6 is 36, and that's going to change to positive 36 because of the I squared, which is just going to change that negative to a positive, right? So as we can clearly see, this 42i and 42i will cancel, which is actually pretty nice. And then we're going to have 35 minus 12, which is going to be equal to 23 over 49 plus 36, which is just going to be equal to 85. And then 30 plus 14, which is just going to be equal to 44 over 85i. And that would be the result of the division of those first two complex numbers written in standard form, which is actually not too bad once you get the hang of it. Since we are working with complex numbers, obviously there might be other operations that the set of complex number has that the set of real numbers might not have or even need. The first of these being conjugation. So the conjugate of a complex number, which we're going to write as z with a bar over it. So this is read as the conjugate of z. So what is z? So let's pretend that z is the complex number x plus iy, where x and y are the real and imaginary parts. And let's assume we want to conjugate that. We're going to define this to be equal to the complex number x minus iy. So the only difference is the imaginary part is just going to change sign, right? So change sign of the imaginary part of that complex number. That's it. So basic example, if you have 5 minus 2i and somebody says, what is the conjugate of that? You're just going to be like, okay, that's just 5 plus 2i, nothing more. And you're like, well, why would I need such a basic operation? There's actually one theorem that actually gives you some insight as to why. So this theorem says if you multiply a complex number by its conjugate, you always get a real number, and this is going to be true for every single complex number z, which can actually be quite useful. So how can we prove this? Because this is true for all, really? Okay, let's see if that's true. So let us assume that z is equal to x plus iy. Well, if z is equal to x plus iy, that means the conjugate of z is going to be equal to x minus iy. So what is z times z bar going to be? And keep in mind, we already know how to do the multiplication of complex numbers. That's going to be x plus iy times x minus iy, treated practically like a foiling problem, just like we did in the set of real numbers. So this is going to be equal to x squared plus ixy minus ixy minus I squared y squared, and keep in mind I squared is equal to minus 1, so we're just left with, since this middle term cancels, it's just going to be equal to x squared plus y squared, and since x and y are an r, x squared plus y squared also is an r, and r is closed under addition, therefore this is an element of r. In particular, the imaginary part of z times z bar is always equal to 0, and this is true for every z in C, is practically what we have here, or we can end there, but that's just some clerical thing that you could say. So you're like, okay, well, when would I ever use this? And we actually already have, because keep in mind, if we have, for example, z1 over z2 there, what we did was multiply by the conjugate of z2, and we're like, okay, we have z1 times z2 conjugate, which is just some complex number over z2 times z2 bar, where this bottom is just a real number, and then we can divide that into the real and imaginary part of z1 times z2 conjugate, and that gives us the standard form for our particular division of complex numbers. Right? And another basic theorem, just for you to try, and this is actually pretty easy, is that when you take a complex number and you add to it its conjugate, you are always going to get the real part of z times 2, right? So this is always going to be true, and actually I invite you to try and prove this on your own. Now, there's one other thing that I want to mention because it's very important when it comes to understanding the basics of complex numbers, and that's the absolute value of complex numbers, right? So keep in mind, if you don't exactly know what absolute value is, absolute value of some number x and c, or you can say x and r, is just the Euclidean distance, the Euclidean or typical traditional distance from the point x to 0, which would be the origin in the case of R2, right? So if we sort of draw a picture of what's going on here, right? Because keep in mind, this is going to be the real part of a complex number. This is going to be the imaginary part of a complex number. Let's assume that we have some complex number over here, z, right? And let's assume that z is equal to x plus iy. So if we sort of connect the origin to this number z, this distance would be the absolute value of z, right? So exactly how do we find that? So what we can do is we can sort of drop a vertical line here and make a right angle. And what we have here is a right triangle. So we know that this distance here is going to be x, the real part. This distance right here is going to be y, the imaginary part. And we know that since this is a right triangle, this satisfies the Pythagorean theorem, which says that x squared plus y squared is going to be equal to the absolute value of z, the quantity squared, and then we can take the square root of both sides, and we're going to have that the absolute value of z is just going to be equal to the square root of the square of the real part plus the square of the imaginary part of that particular complex number, and that's how we would define the absolute value of a complex number. And keep in mind, even though z is complex, this is still a non-negative quantity. Right, so let's just do a quick example just to close this discussion out. Let's assume that z is equal to 3 minus 5i, and somebody asks you, what is the absolute value of z? So the absolute value of z is going to be equal to the square root of the real part squared plus the imaginary part squared. Keep in mind, don't include the I there. And that's going to be equal to the square root of 9 plus 25, which is just going to be equal to the square root of 34. So that's going to be the absolute value of 3 minus 5i. So those are some of the basics that you definitely should know when it comes to working with complex numbers, but there's several other beautiful results for which we'll discuss in the future. Hope you enjoyed this video, and I'll see you in the next one. Take care.